Well, in these kind of models, they were developed back before they discovered Hubble's law. There were some problems, and one of the problems associated with these kind of models is Olber's paradox. Now, what's Olber's paradox? Olbers was an astronomer who first stated the paradox. That's why it's called Olber's paradox. He didn't really first state it. Actually, it was stated a lot earlier than that by several other astronomers. But he got his name tied to it somehow or other, and everybody refers to it as Olber's paradox. Olber's paradox is has to do with the idea of if you had a universe that wasn't expanding, and it had a constant number of, or a constant density of sources in it, if you went out to longer and longer wavelengths, not longer, but went out to greater and greater distances, I'm sorry, the number of sources that you would encounter as you went out there would increase as the cube, because volume increases as the cube of the distance. But the energy that you receive from those only falls off by the inverse square law, so it only falls off by the inverse square. So that when you add up all the amount of energy being received from an infinite universe, you would come up with an infinite amount of energy. In other words, the whole night sky, or in other words, if you looked out far enough, you'd eventually see a star, no matter which direction you looked. You look just a little bit off from the direction you'd looked previously. And so you don't see that. The night sky is dark. It's not constantly bright, and that's Olber's paradox. How can that be? Now, Olber's tried to solve that by saying there had to be material that was absorbing the light between the galaxies, and but modern day scientists say that wouldn't work because that material would quickly be heated up and be completely ionized and radiate and would be very bright and would still not solve the problem. But it turns out that if you were to include in the theory of this redshift, of calculation of how much energy is being received, if you include the redshift into that, you would see that the most distant object has been redshifted so that it has a very infinitely long wavelength, or therefore zero energy, and so it wouldn't be observable. So the solution to Olber's paradox is to put the redshift into it. And that's the way the Big Bang solves Olber's paradox, essentially, is that you can't see an object that's infinitely far away because it's traveling away from you so fast it's disappeared. And it turns out that you can also solve that by having a Compton effect cause a redshift, provided you don't have the electron re-radiate that energy. Now, of course, as Reber's pointed out, the electron will re-radiate some of that energy, but it's important to see that it doesn't re-radiate at all. And the way to see how the Compton effect can solve Olber's paradox is to look at that Compton effect process not from the standpoint of the photon and what happens to it, but from the standpoint of the electron. Now, the electrons between galaxies see radiation coming from all directions and at all wavelengths simultaneously from all kinds of stars. And as a result of the radiation coming from this direction, the electron will want to go that way, but there's some coming from this way and will want to go this way. And so what happens is that there's a general vectorial canceling of these forces, and the electron will accelerate, but generally from away from the brightest nearby sources pretty much. And it will therefore have absorbed energy from some of these photons without a corresponding increase in velocity. And it's a conclusion of the theory of special relativity that if an object absorbs energy without a corresponding increase in velocity, it has to increase in mass, according to E equals mc squared, the famous relationship. So the solution to Olber's paradox that is presented here for this static universe theory is that the light that's being absorbed, that's losing energy to the intervening medium is not re-emitted, but is converted back into mass. The electrons get heavier and heavier, and slowly drift away to the less bright areas of the universe, where they provide the material to create new galaxies. This is kind of Kierein physics here. It's not necessarily, it's kind of heretical physics maybe, but it's new physics in a way, because nobody has ever really described how electrons can go to higher energy levels and increase this way, but it also is consistent with the special theory of relativity. And the interesting thing about this is that before they discovered Hubble's law, there was a group at the University of Chicago that was concerned about Olber's paradox, and it was headed by a Professor Macmillan. And Professor Macmillan came to this very conclusion, that mass has to be being increased between galaxies in order to solve Olber's paradox. And that was the solution that was really given. And we're coming back to all these old and wonderful ideas, and we shouldn't forget the old masters that came up with these. Well, there's a model of the universe, of a static universe, that was developed by Einstein, and it's called the Einstein static universe. Now you can have any kind of static universe. You can have a Euclidean universe where it extends on to forever without ending, or you can have the kind that Einstein developed. And Einstein's static universe is a good model of a static universe, and I want to talk a little bit about the stability of that kind of universe. In Einstein's universe, if you went out far enough, pretty soon you're back where you started from. In other words, if you started at a point here like this, and continued on with a test mass, you would eventually arrive at back where you came from. This is called a model of a universe that is unbounded but finite. So there's only a finite amount of material, or only a finite distance you can go before you're back where you started from, and there's only a finite amount of material in that universe. Yet you never fall off the edge. There's no bound to it. And it's like the surface of a sphere. It's sort of a four-dimensional sphere where you start out on the surface of the Earth, and if you kept going in a straight line, pretty soon you're back where you came from if you went all the way around the world. And this model of the universe is a good static universe model. It's not the only one, but it's a good one. And what happens that causes this this mass to come around back where it is that it follows the path of least resistance. Essentially, it goes along an equipotential path, and it's the mass is deflected by both gravity and radiation pressure, and eventually it comes back where it started from. And the distance that it goes is a function of the amount of mass in the universe, and it's also a function of the amount of radiation pressure in the universe. In other words, the radius, sometimes called the radius, it's really more a circumference, but it's essentially called the radius of the universe, is a function of the total amount of mass or gravitational potential in the universe and the total amount of radiation pressure that an object sees. And when Einstein developed that, there weren't any problems to it. But after they discovered the redshift, everybody said, well, we should have thought about that. You know, such a thing is not really stable. If you had, for example, a change in the amount of mass in the universe and a change in the amount of radiation pressure in the universe, then the radius would change. It's not a stable, static model to processes. And we observe processes in the universe all the time. Stars are converting mass in the sun and in stars to light, and therefore that causes the amount of mass to decrease and the amount of radiation pressure to increase. And if that were to occur, that would cause the radius to change, which should therefore cause a big bang or a big collapse. It turns out that in this the model that's all well worked out, that if you take the process that's the observed process, which is the conversion of mass to radiation pressure, then the universe collapses rather than expanding.